title. What I actually would call it now is capitalistic and system conform and talk about encryption. Because I gave this, I made the title when it was 2 days after Heartbleed, I think. And in the days following, everybody was talking about encryption and how we need to protect ourselves against state surveillance. And this is totally not what this talk is about. This talk is about just SSL. My name is Armin Ronacher, and I'm mostly doing Python software development, but as my day job, I work as an independent contractor for Fireteam, which is an online services company in London. And we do online infrastructure for computer games, and one of the things you want to do there is keep things safe, not so much because you're afraid that people steal your stuff, but because you want to make it as hard as possible for computer gamers to game the system, so you just encrypt everything. So this is basically my background of why I'm talking about OpenSSL. And this is a talk with a lot of slides, so I don't actually know if this will fit in time, so bear with me. So we start with the problem with programmers, which is that they think everything is a technical problem, and this is basically what this talk is about. The idea of this talk is to explain you that encryption is important, but there are many more important things about keeping things secure. And the most important part is what fraud is about. So you recognize this thing. It's a credit card number. This is the part where we said this is safe, so the last 4 digits, nobody can do anything useful with it, allegedly so. Except that some people bind trust to the last 4 digits of a credit card number as well, so sometimes they will ask you, what's the last 4 digits of a credit card number to reset your password, which is something you can get from another website, because they also say that's safe information. Or they pick the first 6 or something. But the nice thing with a credit card number is they're completely insecure. What makes them secure? Well, nothing. They're just 16 digits. And the reason why credit card numbers still work for us is because we have accepted that things will be stolen, and there will be criminals that make terrible things with you. And they will steal your identity, your credit card numbers, and so forth. And the question is, what damage can they actually do when they steal your credit card number? And they can do some damage, but your credit card company will basically try to protect you against some of the damage by having an insurance for the amount of money that can be stolen with a credit card before you cancel the credit card, which is completely different than Bitcoin. So Bitcoin has a strong encryption, 265-bit private key, and it's completely decentralized. It has all the nice properties of a secure payment system, but I still rather lose my credit card number than my Bitcoin private key. And the reason for that is obvious, because if someone steals my Bitcoins, the system in itself, in the trust, is established that the person that owns the private key is the ultimate decision maker about where the money goes. So if someone steals a Bitcoin private key, your money goes to whoever stole your key, which is bad as a user. But it's completely secure, because they use the most secure system in the world, most secure currency in the world to steal your money. So encryption, in this case, doesn't actually help against a hypothetical attacker. So the reason why credit cards kind of still work is because when they started out, there were like maybe 100 people that had a credit card somewhere in some city. And the credit card literally was just a card with a number. And you go somewhere and you sign a check. And because you always go to the same diners club, they will recognize that your face goes to this card. And if someone else comes with the card, they will look suspicious. But now that we have credit cards over the internet, everything looks a little bit different, because you don't actually see who uses the card. But we still have accepted that credit cards will be stolen, and we kind of protect against this. So the protocol of a credit card with a credit card number is completely insecure, but the whole payment process is absolutely secure. Because if someone steals your credit card, it's terrible, and it probably will cause you all kinds of problems, but it's not the worst thing in the world. Basically, if your fraud is smaller than your transaction fees, it kind of works out positively. And this is just an example. It's too easy to forget the bigger picture. So credit card numbers are insecure, but the whole system still works. So, and this leads directly into this whole thing of people need to be understanding what all this stuff means as a customer. So you all know lock symbols. They appear somewhere and they make something secure. And these lock symbols have appeared not just in browser Chrome, like in your URL bar, but they also have appeared on login buttons and everywhere where security is. So the user associates the lock symbol with security, not really understanding what this actually means. But the same thing is happening with encryption now. So when I think WhatsApp was acquired by Facebook, and then all of a sudden there was like this outrage, oh, they're going to get all my data. So let's use Telegram, which has like secure encryption and things. And then there's Chatter, which is supported by McAfee, which also has encryption. But just by having encryption doesn't actually make it safe. For something to be secure, you need to follow a whole bunch of properties. So just because it's encrypted doesn't mean it's safe. And in fact, now that we actually use encryption so much, there's much more interest in trying to break the encryption. And in the last 3 years, like there was this whole, I don't know, demolition of the SSL standard by punching all kinds of holes in it. And I think barely any developer understands how the system works anymore. And all of this doesn't work if the user doesn't understand what the good lock symbol is, like the one in the browser Chrome, and what the bad lock symbol is, the one in the browser bar. Or what good encryption is, which would be end-to-end, where someone has verified this actually works, versus bad encryption, which is just a lock symbol in your browser, surprisingly enough. But even developers are not actually sure yet how encryption works in many ways. I think this is the most disappointing thing. It's especially visible now that more and more people start using encryption in all kinds of situations. So most important, remember why you encrypt, like what does encryption actually give you? Because if you put an SSL certificate on your blog, what did you actually gain from it? I've seen this a couple of times, people putting their blogs behind HTTPS. Why? The one thing it gave you is that when you had a heartbeat affected server, it would just randomly give you out some secrets that were in the server, which made it less secure. But you need to protect something for encryption to make sense. Otherwise, you're just setting a political symbol. So why do we encrypt traffic? Any ideas? Why would we encrypt traffic? And since when are we actually interested in this?
Because there is sensitive information.
Probably. But actually, the only reason why we care about Wi-Fi, why we care about encryption is Starbucks. Because before Starbucks, there was not really any public Wi-Fi. Before there wasn't any public Wi-Fi, there was no way to realistically attack an encryption unless you just walked in somewhere and put a fake router in the system. I mean, it was possible, but it was much less likely. But public Wi-Fi killed the unencrypted browser session because basically nowadays all you need to do is you need to sit in a McDonald's and you put up your laptop and you start, I don't know, Firesheep or something, and in come all the session cookies of people around you, and you just sign in and do crazy things with their accounts. So the attacker came from secret agents to idiots. It made it just too easy to target someone, and basically it means you didn't even need to target someone, you just sit at McDonald's and you get session cookies from everywhere. And from very low probability that someone would ever attack your data, it went to very high. Because now you sit at an airport and you feel insecure, which a couple of years ago before was not really the case. Back then, encryption was quite literally to protect your, I don't know, credit card transaction. And now Facebook needs encryption because people otherwise run away with your private pictures. So what you need for encryption is an encryption system. And what encryption gives you is this protection against eavesdropping. And there are two forms, as most people know. There's the passive one and the active one. Passive one means someone has a cable connected or a virtual cable connected to a transaction, to a transmission of data, and they can decrypt the traffic. That's what encryption protects against, because even if you don't know which the two endpoints are, encryption will make it impossible for you to read the data unless you have manipulated a key. But for active eavesdropping would be when person A, instead of talking to person B, a secure channel, would talk to an arbitrary attacker in between who decrypts the traffic and then re-encrypts it to the other person. So unless person A and person B have a chance to be 100% sure that they are talking to the right person, they wouldn't be able to detect an active eavesdropper who was sitting in between decrypting and re-encrypting. So how do you protect against active eavesdropping? And the only way to do that is to verify that you're connecting to the right thing. How many of you actually SSH into a server and check that key on first time? Hands up. 2 people in this whole room. Yeah, well, see, this is pretty much the point. So developers don't even check fingerprints. So how do users check fingerprints? The answer is they don't. They don't even know what a lock symbol is. So how do they know how to verify a fingerprint? How would they even know which fingerprint they should verify against? And basically, it doesn't work. People have understood this, and they have introduced this concept of a certificate authority. And a certificate authority means that instead of me going to a server, looking at the fingerprint and making sure it's the same, I use software where the developer of the software has trusted another party to verify the trust of another person. So if I want to say I have the domain boku.org, I pay money to a person who checks my passport, who verifies that I am that person and have at that point in time controlled that domain. That person has paid money to Mozilla to have their certificate added there, and Mozilla then is a browser that lots of people are using who trust that certificate authority. So it's basically just a distribution of this problem. And it did work good enough when we had 100 websites on the internet. Now that we have millions, and each new person adding more SSL and encryption into their websites are making this whole problem bigger by putting more and more load onto the certificate authorities. Because if you look at the Cloudflare blog post they had recently, where they showed how many certificates they had to revoke after Heartbleed, that number was insane. We have so many SSL users now that CAs are getting less and less useful because it becomes just too much work to verify. But the most important thing is that CAs are completely worthless for securing APIs. And I don't understand why we still support this whole idea of a CA for like APIs, but apparently it's a thing. So if you connect to, I don't know, api.facebook.net or com, or whatever they have, you sign in and there is an HTTPS endpoint, and it's protected by a certificate signed by some random CA. Facebook doesn't even tell you which one it is. Why do they do this? Like, unless you're JavaScript, there's no reason why you can't just verify the fingerprint. It could be in the Facebook documentation. My fingerprint is going to be this thing, or if you say, this is the certificate to use, this self-signed certificate, this is the only thing you need to use, just trust this one. And if they have a problem, they can revoke it and change it. But instead, we use this absolutely pointless certificate authority system on top. So how would you actually completely securely protect an API endpoint or a service to have secure communication between 2 endpoints? And I'm not talking about JavaScript or browsers, which are just its own thing. There's only one rule to follow, which is you run your own CA. You issue certificates for 24 hours and not longer, and you only trust your own CA, and you screw revocations. Like, this whole idea of revoking certificates is just fundamentally broken and has been for years. Browsers don't even support, like Firefox might support it, but most browsers don't even support certificate revocations because they're just, they fundamentally don't work. Like, the idea of a certificate is it's valid from one point and it stops at the point in the future. So if at any point in time the future, this future date is no longer valid because you lost your certificate, then any user of this certificate would always have to check that the certificate is still valid, which in other point is you don't even need that certificate, you just constantly ask the service if it's still valid. So the way to get around with destroying the whole system is you just issue certificates for a really short period of time, which means that if that certificate does actually get lost, the damage is resolved automatically in less than 24 hours, because however long it takes a certificate to expire naturally. Your root CA is valid for 20 years or so. If you ever lose that one, yes, you need to make a new one and send out every of your customers their new certificate. But you don't have to deal with any revocations, any of the other stuff. This is the most secure way to run it with an SSL system as far as I know. But obviously it doesn't work with browsers. But this is easy. There's nothing that can go really wrong with it. And we should actually be encouraging this to be used as a concept. So you only trust your own CA. You don't trust anyone else. Because there are nowadays, I think there are like 180 publicly signed certificate authorities, some of which are run by organizations that have shown in the past that they issue wrong certificates, but because they're literally too big to fail, they're still valid and not revoked. So you trust your own CA. All of your API clients only trust that CA, and that's it, nothing else. And if it gets compromised, you issue new keys. And as I mentioned, if the keys individually get compromised, they expire anyways. So if you use Python, this is all you need to know. You use the request library, which thankfully can, instead of trusting random CAs, can trust a single one. And it's just a file with the certificate authority of the CA you want to trust, and that's it. And you have secure communication between 2 points. Like between an API and something else, and it works and nothing can go in between. But this is the thing, when we started doing this with Fireteam, which is the company I work for, we noticed that it breaks. And the reason why it breaks is mostly Windows users, but that's because we make computer games, so there are lots of Windows users, but they have these things called antivirus solutions. And they have this problem, they need to scan downloaded files to see if they're bad. So what they do is they demand in the middle your SSL connection locally, which breaks everything. But the way they do this is they add their own certificate in the system store. So when I go to my bank website on a system that has this awesome antivirus solution running, instead of going to the bank website, I go to a local proxy, which decrypts my traffic, sends it through the antivirus solution, re-encrypts it with a fake certificate that looks like it's from the bank, and then goes out into the internet. They even fake these little blue bars and green bars and all this stuff in the browser, and it looks just amazing, so you don't even notice that you're being man in the middle on your own computer. But it means that if you have your own certificate you trust, that obviously doesn't work, because your system, in our case, our computer game, would just say, this is clearly man in the middle. Someone destroyed this connection, I'm going to drop you. But if you actually, this is the problem. People are working against encryption, sort of, out of principle, and it is just absolutely frustrating. So we ended up not being secure. We ended up using publicly signed certificates because it was just too much of a hassle to convince Windows users to uninstall their firewalls. But I mean, this is literally part of the problem, that it came so far that people do this stuff. Yeah. So certificate authorities are now are widely being discussed, especially due to Heartbleed. Not so much because people just realize that certificate authorities are terrible, but because revocations don't work. And because revocations don't work, it means that if you actually lose your key, you open, the door is open for until the certificate naturally expires, which is really not a good thing, because certificate authorities make the money every time you sign a certificate, which means they sign it for long enough periods of time that you pay them again, but short enough periods of time that you have to go back to them. Doesn't make sense. But in any case, they sign it for a year. That's what runs out. And so every year you pay them $100, but you can't sign a certificate for every day, because otherwise you could pay $100 every single day. So if you would want to have certificates that expire really, really quickly, you're going to be a broke man. But with Heartbleed, now all of a sudden we discovered that this whole revocation system is fundamentally flawed. So everybody who actually lost a certificate probably still has a lost certificate, and someone could be impersonating them right now. I mean, some browsers do some checks, but not really much. So hardly used CAs are broken. But why exactly are they broken? The main reason why they're broken is because we have so many of them, and they need to verify so much trust. So basically, any certificate authority on your browser can vouch for any identity on the web. So it doesn't matter that Google right now is being signed by VeriSign or themselves, or whatever they're being signed by. If a random other CA in your browser would also say, well, actually, I have another certificate, this is also Google, your browser will just trust it. there's inherently nothing in the system would prevent this from happening. And basically, it means that if they have one shitty employee in one shitty CA, then you're already like lost. And it's worse because there are two types of certificates. There are the ones that are regular for one specific distinguished name, but then or common name. But then you have also certificates that can sign other certificates that can act as a chain, as an element in the certificate chain, which means that. So yeah, there was a company in the Netherlands where pretty much exactly this happened. And it's pretty bad because there's no protection against, like, you would say like, oh, it's just one certificate, so maybe they can man in the middle Google, but then they can't man in the middle Bing, so just search on both of them or something. But it's actually worse than that because they only need to have one certificate signed that has the root CA bit set, and then the attacker can sign as many certificates as they want. So it's really, really bad. And that's because there is not really any sort of scoping in this whole system. You can't say that everything below google.com now has to be signed by this specific certificate. There's just nothing in there. Because what you actually would want is, I trust the one specific CA to vouch for a certain domain, and then everything below that is being only signed by that company. Because otherwise it's just random in a situation where you need to trust everything in the system. And we're kind of moving this way, I think, at one point in the future when people have agreed on how this should be solved. To solve this particular problem, I think the closest we have seen so far is certificate pinning, where once you have seen a certificate once, you kind of want to see this again. But then what happens if you change your certificate provider? It gets a little bit weird.
You do know Chrome does this for some of the...
Chrome does this for all Google domains. And for Twitter and Facebook and for some big ones. But unless you're a big player in the field, you're kind of screwed still. So it's like patching things on top of a fundamentally broken system. But yeah.
Isn't HSDS something?
Yeah, I think that's so HSDS was an extension initially where you could say, you cannot remove HTTPS from me once you have seen that there was HTTPS on me. So if you go to https.facebook.com, and later on someone would say, actually, there's http.facebook.com, then your browser would say, no, because Facebook said it's SSL, I will only ever go to SSL now. Because otherwise you just remove the encryption, quite literally. If you're an attacker, you just say, oh, https.facebook.com is gone, now it's http.facebook.com. So, but they are trying to extend this, or already have done, to force certain certificates also being used. So, or keys. Yeah, so stuff is being done, is being changed, but I think this is at the moment definitely a moving field. There have been alternative proposals that are much more interesting than supporting certificate authorities forward. For instance, one of the ideas was that the most realistic approach to attack a server is by man-in-the-middling a user very, very locally, like on the Wi-Fi, because that's the most realistic spot to attack a user. Because most people are not being surveyed by NSA, most people are being surveyed by their neighbors. So one of the proposals that came from, I forgot who actually came up with this, but was the idea to use network perspectives, where when you do an HTTP request, you go to a server, but you also ask a whole bunch of other servers to do a similar request to see if they all come up with the same certificate. And if you see that the servers come back with different certificates, then something is clearly wrong. And the way this would be implemented is by sort of the same way as the Tor network works. You encrypt more and more things into itself, so that if you go to one of these notary servers, they wouldn't necessarily know which direct server you came from. So they would only see, they would go through a chain of servers. Because otherwise you end up in a situation where, in order to verify that Facebook.com has the correct certificate, everybody of your notary servers would know your IP address, just wanted to go to Facebook. So that's something you clearly want to avoid. But maybe this would change. But at the moment, if you already start becoming less reliable on certificate authorities, it would be nice. Because for APIs, for instance, there's really no reason why you should use publicly signed ones, unless you absolutely have to use JavaScript to talk to it. But I think the biggest problem is that we're using a system that was made for very, very small amount of people, and has only ever been audited by a very small amount of people. And now we're putting more and more emphasis on the whole thing, and it just becomes very obvious that everything in so many ways is broken, that not enough people have looked at OpenSSL, which is the most popular implementation of SSL. All the best practices out there for actually protecting encryption, your browser session, are probably just copy-paste from someone else's best practice. Like, there's just not enough common understanding among regular developers how to do security. Just having a certificate on your browser is not, on your website is not the solution. Self-signed certificates are not bad. The problem is browsers started making them really, really terrible, so everybody thinks they're terrible out of principle. But for a lot of things, self-signed certificates are the most secure thing you can do. Because you know, if you verify this fingerprint, you know that you're connecting only to this thing. Certificate is just fine. Never ever look at OpenSSL source code if you're a normal human being, unless you work for, I guess, the OpenBSD guys, which are currently taking this whole thing apart. It's absolutely disgusting. It's not just bad from a software development point of view, it just looks really ugly. It has completely inconsistent APIs. All the defaults are just wrong. It's impossible to use it securely, which is just really disappointing. And then people put patches on top of this thing to make it even worse. For instance, with Apple, we have discovered that you cannot not trust the system store. Even if you say, I only trust this CA bundle, it will still trust all the certificates on your system, because they have a little patch which just puts the keychain support in there, and you cannot disable it. Request, the Python library by default just trusts all certificate authorities, which is hilarious given that this is a tool used to talk to APIs. Why do I have to trust everything? Really, in my opinion, request should give you an HTTP, it should give you a programming error if you try to do an HTTPS request. It should ask you very explicitly, do you want to trust all certificates or just a specific one? And I think the best thing is with Heartbleed, for the first time, we had SSL support being less secure than no SSL support, which is really quite an accomplishment. Yes, but all of this really boils down to we are growing at really crazy rates, this SSL system, from barely being used at all to everybody's using it. And with this whole security NSA craze, we're growing even faster, which is probably going to cause a whole bunch of more problems in the future. Credit cards were made for 1,000 people, certificate orifices were hundreds of sites. Now we're just exploded with all of this. Just look at how many revocations people tried to do after the Heartbleed bug, and you can get an idea of how many SSL encrypted sites are actually out there. It's a lot. And OpenSSL, our most widely used library, was completely improperly audited so far. And if you want to have a laugh, look at the OpenSSL Valhalla Rampage website, which is full of commit messages by OpenBSD maintainers trying to make sense of the library. And they have amazing things in there, like I give up, reuse problem is unfixable, DLV says Puppet crashes. And what this actually means is that I don't know if you remember Heartbleed, it had this thing where it gave you random memory from the server back. Why does it give you random memory from the server back? Why does it not crash? They have their own allocator, which doesn't open pages on the operating system back to the pool, which means that previously used memory stays accessible with a very high chance. And because that was the case and never crashed, people started to rely on this, which means that even in OpenSSL, people started to rely on previously used memory still being available. So when the OpenBSD people tried to fix this problem, they discovered that more and more client code relies on completely insecure behavior, and they can't even fix it properly now because everybody starts to rely on this. It's just such a fundamentally broken system that it's just really hard to see a bright light in there. So basically what I want to say is plan for failure, plan for things going wrong, plan for you cannot revoke a certificate, plan for user getting the data stolen, all that kind of stuff. Try to hedge against something just not working in your favor. You need to consider what happens when a user gets hacked because his data gets intercepted, and keyloggers are still a thing. Even if you have SSL encryption there is still a certain chance that someone has a little program running on his computer stealing his password. And if that user then loses his identity and you don't have a way to protect the user, that's probably a problem. And you need to consider also what happens when your data gets stolen. Like, I don't know if anyone ever implemented a payment gateway thing, but there's this PCI specification of things you have to do to fulfill the data requirements. And while they might sound really ridiculous, they actually put such a high barrier on credit card transactions that you end up in two situations. One of them is you just run away screaming because you don't want to implement this. The other one is you actually do it. So you're one of the ones that didn't run away screaming, so there are probably less and less companies actually implementing credit card transactions. And the third one is, if you do not follow these rules and someone gets his credit card data stolen, they come after you and charge you ridiculous amounts of money. And that's how they get the money back for the transaction fees. So basically, my point is, consider what happens if stuff gets really bad because your encryption is not reliable. Do not trust that your encryption is going to solve all your problems. Just consider that something will happen and you better not suffer from this because people start suing you for it. Yes, that's basically it. Encryption is hardened security. It should not be your only defense. And feel free to ask questions.
You were talking about using certificates only for 24 hours.
Yes.
And that it only was applicable to APIs. But isn't it possible to actually have a certificate authority sign you a certificate that you can use to sign your own short-lived certificate?
So that would be nice if you could get a certificate from certificate authority to sign more certificates. Because the only way this would work is if you could say the certificate they gave you is only valid for your own domain and subdomains of it, which is currently not possible. That would solve a lot of problems, because then we could start doing this. But at the moment, unless you're Google size and have your own CA in this whole thing, I don't think there's a way to sign short-living certificates.
In the handshake of SSL, you give a certificate, but if your certificate revokes or ends every 24 hours, do you have to overlap, or can you just?
Yes, you have to overlap. You need to basically have an overlap period where where these short-living certificates currently is being implemented is not SSL. It's actually so the first thing is you trust the root, so it doesn't actually matter that the certificate expires, because you don't send the client certificate. What you actually send is the client goes through the handshake and then verifies with its local certificate authority. And that isn't not for 24 hours, that's for 10 years or so. It's just one certificate in there. So it doesn't matter that the other one revokes all the time. But one place where this very short revocation thing is implemented is Google's identity trust forwarding thing. So if you sign in with Google ID somewhere, and now you're signed into the service, but the service wants to hand this trust over to another party. They do this with, there's an already signed JWT, and you hand this over, and to verify this, the certificate is really only valid for a very, very short amount of time. So that if something, because Google knows nobody checks for revocations, so they want to lower the risk of certificates, keys being stolen. But for the handshake, it's not a problem, because you don't ever trust the certificate. You couldn't do it with client credentials. If you would send client credential certificates in, those need to be valid for a long period of time, because you can't hand in two. At least I don't think you can hand in two.
So the thing that you talked about with SSH keys and checking their fingerprint, basically, I think a lot of people didn't maybe raise their hand because you create like a server online, and then you connect to it for the first time, and it's like, yeah, well, I just requested the server, and now it's there, and yeah, I didn't have any knowledge about it beforehand, so I just have to accept it. So basically, you also would need to have some kind of off-band way of getting the fingerprint of the server key of the server you just asked for online.
So yeah, especially so yes, you need to know your fingerprint before you can connect to the server, which is especially funny currently, given that we're moving away from physical machines. So you already have the server made by a cloud provider. So where do you actually get the fingerprint from initially? Like, the server could already be wrong at the time it arrives at you. So it's really a hard problem. You can only lower the risk of that being wrong, unless, I mean, it's like sometimes it's really funny because a lot of the security protocols that are in place are made with good intentions and then really badly executed. We had a client to work with who gave us access to their VPN, and they were very clever. They gave us the access, the username, so they gave us the authenticator first, and then the password and usernames in separate emails, and their IT department clearly said, do not send it by email. So what they did, they held up the picture on a Skype camera, of which one of our guys made a screenshot and then sent it by email. It's just, it's like stuff like this happens. So what they should have done is take it into the plane and fly it over, I guess. That was the intention, but that didn't happen. So yeah.